It is late November 1943, somewhere on a deteriorated dirt road in eastern Ukraine. The temperature is hovering just above freezing. In those vehicles, a mechanical breakdown on a secured road triggered a simple, reliable protocol. The radio operator would signal the maintenance company, the rescue vehicles down into the ditch with it. This mechanical paralysis happened in a vacuum, assuming the recovery was peaceful. But a battlefield is never peaceful. If Soviet artillery began registering the bottleneck, or if attack aircraft spotted the massive, slow-moving column, the mechanics had only minutes to make a terrible choice. They could not speed up. They could not take evasive action. They were physically pinned to the earth by the very machine they were trying to save. The physical environment, not enemy armor, became the ultimate arbiter of a heavy tank survival. The multi-vehicle towing system was a desperate improvisation that only functioned when the ground permitted it. But that mechanical limitation did not stay isolated to the maintenance yards. If a heavy panzer could only be rescued from wide, solid roads with shallow gradients and strong bridges, then it could only be risked near wide, solid roads with shallow gradients and strong bridges. What the men on the ground experienced as a nightmare of mud and steel was about to become an operational straitjacket for the officers planning the war. In a dimly lit command post miles behind the front, a German battalion commander traces a grease pencil over a topographic map. He sees a vulnerable Soviet flank positioned across a wide expanse of forested marshland. Tactically, it is the perfect avenue of approach. A single heavy half-track would arrive, hook a steel cable to the towing eyes, and drag the medium tank back to a field workshop. His heavy tanks could easily overwhelm the light infantry holding the sector. But the pencil stops. The commander does not draw the arrow through the woods. Instead, he routes his armor straight down a heavily defended, highly visible causeway. He makes this choice not because he fears enemy artillery, but because he fears the ground. He knows that if a 56-ton Tiger breaks a track in that marshland, it will sink into the soft earth. He knows his recovery platoon, equipped with their lighter half-tracks, will never be able to navigate the mud to reach the disabled vehicle, let alone drag it out. A single, routine mechanical failure in those woods would mean the permanent loss of an irreplaceable machine. The invisible system required to sustain heavy armor had begun to dictate how that armor could fight. The Tiger was originally conceived as a breakthrough weapon, built to shatter enemy lines wherever they were weakest. But the extreme mass of the vehicle, combined with the severe limitations of the multi-vehicle towing chain, turned that aggressive doctrine upside down. The heavy panzer battalions became strictly tethered to the physical infrastructure of the battlefield. A battalion commander did not just deploy tanks. Mechanics would replace the shattered gears, and the crew would be back in combat within 24 hours. The system was organized, practiced, and highly efficient. He deployed a fragile, cumbersome logistical tail. Every time he committed his armor to an attack, he had to calculate not only the enemy strength, but the precise route his recovery vehicles would take when the tanks inevitably broke down. He had to husband his prime movers carefully. A heavy battalion might boast 45 Tigers on paper, but it was authorized only a fraction of that number in heavy half-tracks. If those recovery vehicles were tied up dragging one tank out of a ditch, or if they sheared their own transmissions under the strain, the entire battalion lost its safety net. The result was a profound paralysis in operational planning. German officers became incredibly cautious with their most powerful weapons. They restricted their heavy armor to paved roads, dry fields, and gentle gradients. They actively avoided sending them into deep mud, narrow city streets, or dense forests where recovery operations would be mechanically impossible. The opposing armies quickly noticed this behavioral shift. Soviet and Allied commanders did not need to understand the exact gear ratios of a German half-track to exploit its weakness. They only had to look at the local geography, because the heavy German tanks were confined to the best roads and the most solid ground. Their avenues of approach became rigidly predictable. Allied forces simply laid dense minefields across the main causeways. The commander expects this exact sequence to unfold for his Tiger. He logs the time, radios the coordinates, and waits, registered their heavy artillery on the widest intersections, and maneuvered around the heavy German battalions in the difficult terrain. The very steel that made the vehicle a formidable opponent also placed it in a geographical cage. Yet, despite this tactical straitjacket, the German recovery crews managed to sustain the heavy battalions for a time. As long as the army was advancing, or at least holding a static line, a disabled tank could sit in a field for 3 days waiting for a towing convoy to assemble. The system relied entirely on holding the territory around the broken machine, but that reliance reveals a much darker reality. What happens to a weapons system that requires a slow, perfectly orchestrated rescue when the front lines collapse and the hours required to build a towing chain simply run out? It is the summer of 1944, and the static lines of the Eastern Front have shattered. A German heavy panzer battalion is retreating under immense pressure. On a dust-choked dirt road, a Tiger throws a track, the heavy steel links snapping under the strain of continuous driving. The crew is unhurt, the armor is untouched. But as the hours pass and the tank settles deeper into the freezing mud, the reality of their situation shifts. The commander radios the maintenance unit, expecting the standard multi-vehicle towing convoy. But the radio returns only static. The luxury of time has vanished. The Soviet vanguard is less than 10 miles away and closing rapidly. The maintenance company is either already retreating, or their few FAMO half-tracks are hopelessly stuck in the chaotic traffic of fleeing infantry and horse-drawn artillery. Even if the recovery vehicles were available, they cannot drive backward against a retreating army to reach one disabled tank. The fragile, synchronized towing chain requires hours of uninterrupted labor, a clear road, and secure territory. A general retreat offers none of these. The crew inside the Tiger faces a terrifying reality. Their 56-ton machine is functionally intact. The 88mm gun is deadly. The Krupp steel is unpierced. But without the ability to move, the tank is no longer a weapon. It is a bunker waiting to be surrounded. Military doctrine dictates the next immediate action, and it represents one of the most agonizing decisions a tank commander can make. They cannot allow their most advanced heavy armor to be captured intact and studied by Soviet engineers. They must destroy their own vehicle. The destruction is methodical and brutal. The crew scrambles out of the hatches, grabbing only their personal weapons and rations. A Panzer IV weighs 25 tons. A Tiger weighs 56. That massive increase in armor and firepower did not just change how the vehicle fought. The loader pulls the pin on a thermite grenade and drops it down the open breech of the main gun, ensuring the intense heat will melt the firing mechanism into a useless block of slag. The driver places timed explosive charges deep inside the Maybach engine compartment, and among the remaining high-explosive ammunition racks, the crew runs for the tree line. Minutes later, a massive internal detonation rips the 30-ton turret from the hull, flipping it onto the dirt. This violent ritual was repeated hundreds of times across both the eastern and western fronts. When historians analyze the casualty reports of German heavy panzer battalions, a startling pattern emerges. A massive percentage of Tigers and Panthers were not destroyed by enemy tanks, anti-tank guns, or aircraft. They were scuttled by their own crews. Whenever the German army was forced into a rapid retreat, a minor mechanical breakdown, a slipped gear, a broken suspension arm. A lack of fuel became an automatic death sentence for the machine. Advancing Allied and Soviet troops frequently stumbled across these steel corpses. They would find a blackened tiger blocking a rural road, cautiously inspect it, and realize that the frontal armor had never been penetrated by a shell. The opposing forces could see the devastating result. It fundamentally altered the physics of what happened when it stopped. Miles away, at the battalion maintenance yard, the radio call is received with dread, but they could not see the invisible logistical failure that caused it. They assumed the tank was defeated in battle, when in reality, it was defeated by its own extreme weight and the fatal absence of 3 18-ton half-tracks. Germany was bleeding its most expensive, most powerful weapons dry, often without the enemy having to fire a single shot. This cycle of self-inflicted destruction was entirely unsustainable. The German military-industrial complex finally accepted that dragging heavy tanks with a daisy chain of lighter vehicles was a strategic failure. The problem had outgrown the field maintenance yards. The question was whether German factories could design and build a specialized single-vehicle solution fast enough to stop the bleeding. Inside a cavernous assembly plant in Kassel, sparks shower onto a pristine tank hull. But no turret will be fitted to this chassis. Instead, engineers are bolting a massive wooden superstructure and a heavy winch assembly into the open fighting compartment. They are building a machine born of mathematical defeat. The High Command had finally conceded the brutal physical reality of the battlefield. The only thing capable of rescuing 56 tons of dead weight was another heavy panzer. This was the Bergepanther, the dedicated heavy recovery vehicle. The mechanics have the spare final drive. They have the tools, but they know a brutal logistical truth that the tank crew is just beginning to realize. The German army desperately needed years earlier. To break their reliance on the fragile, multi-vehicle towing chains that paralyzed operational planning, designers engineered a single-vehicle solution. They stripped the main gun and heavy turret from a Panther tank and replaced them with a 40-ton mechanical winch driven by the main engine. To prevent the winch from simply dragging the recovery vehicle backward into the mud, a massive steel spade was attached to the rear hull. When lowered, this heavy plow anchored the machine firmly into the earth. A single Bergepanther could drop its spade, unspool a thick steel cable, and drag an immobilized tiger out of a deep crater, without requiring 3 separate half-tracks and hours of synchronized labor. The mechanism was brilliant, functional, and entirely too late. The engineering was sound, but the timing was disastrous. By the time the Bergepanther entered production in mid-1943, the German industrial complex was fracturing under relentless Allied bombing and severe material shortages. The factories were locked in a desperate zero-sum game. Every Bergepanther built required the exact same hull, engine, transmission, and suspension components as a frontline combat tank. A factory could build a weapon to destroy the advancing enemy, or it could build a tractor to save that weapon. When 56 tons of steel loses its own motive power, it ceases to be a weapon. It becomes a permanent anchor. It could not afford to build both. The industrial mathematics heavily favored immediate firepower over long-term survival. German logistical planners calculated that a heavy panzer battalion required at least 4 of these dedicated recovery vehicles to keep its armor rolling. The production lines could only trickle them out in fractions. By the end of the war, German industry produced fewer than 350 Bergepanthers to service thousands of heavy tanks across 2 massive fronts. A battalion fighting a desperate retreat might receive a single Bergepanther to support 45 Tigers. The severe mismatch had merely shifted from the physics of towing to the economics of manufacturing. When that single Bergepanther inevitably broke a final drive, ran over a mine, or was destroyed by an anti-tank gun, the entire battalion instantly reverted to the terrifying era of the three-vehicle FAMO convoy. Furthermore, the Bergepanther was not immune to the exact same mechanical strain it was designed to cure. Dragging dead weight through freezing mud burned out its transmission just as easily as the tanks it tried to save. Soon, field maintenance yards faced an absurd, recursive nightmare. Mechanics found themselves trying to scrape together three 18-ton half-tracks. The German army possesses a fleet of specialized recovery vehicles designed to rescue disabled armor, but those machines were engineered for a previous generation of warfare, just to drag their broken 40-ton Bergepanther out of a ditch so that they could eventually fix it to go rescue a stranded tiger. The system was eating itself alive. The attempt to engineer a specialized way out of the crisis proved that the flaw was not simply a lack of proper towing equipment. The fatal flaw was the extreme weight of the armor itself. German industry had created a weapon system that continuously outgrew its own logistical tail, consuming vast resources just to keep its steel from sinking permanently into the earth. The final question was no longer how to save the heaviest armor, but what the ultimate legacy of a weapon is when it becomes too heavy to survive its own environment. On that freezing dirt road in eastern Ukraine in late November 1943, the crew sitting inside their immobilized Tiger waited for a rescue that would define the limits of their machine. They felt secure behind 100 millimeters of Krupp steel, trusting that the heavy gun and thick armor made them untouchable. But they were trapped in a profound illusion. Their pristine tank had already been defeated. It was not beaten by Soviet artillery or an Allied airstrike, but by a shattered internal gear and the clinging mud beneath their wide tracks. Turning the top layer of earth into a thick, clinging mud, a Tiger I of a German heavy panzer battalion is repositioning behind the front lines. The crew, sitting inside their pristine, fully armed tank, believes they are simply waiting for a routine tow. To get that single tank back to a repair yard would require 3 heavy half-tracks, a perfectly straight road, hours of daylight, and a static front line. If any one of those conditions failed, the machine would have to be abandoned. The mystery of the heavy panzer battalions was never really about the thickness of their armor or the muzzle velocity of their guns. It was about the unforgiving mathematics of mass and the invisible logistical system required to sustain it in a physical world. A tank is not a standalone fortress. It is merely the visible tip of a deep mechanical chain. It requires a constant flow of fuel, specialized maintenance, a massive supply of spare parts, and, most crucially, a reliable way to be pulled back from the edge of destruction when its own engine invariably fails. German industry engineered a weapon that pushed the boundaries of lethality, but they ignored the ecosystem required to support it. By building a vehicle that weighed 56 tons without simultaneously building the infrastructure to move it, they fundamentally broke the recovery network designed to keep their army alive. That single failure cascaded upward through the entire military structure. It forced field mechanics to improvise highly dangerous, synchronized towing operations that ruined their remaining equipment. It chained the heaviest armor to the most predictable, solid roads, stripping combat commanders of their tactical flexibility and trapping them in geographical cages. Ultimately, it condemned hundreds of perfectly intact vehicles. They do not yet understand that the ground beneath them is slowly claiming the vehicle. To understand why a minor mechanical failure to be violently destroyed by their own crews the moment a strategic retreat was ordered, the true cost of this unbalanced engineering was not paid by the tank designers drafting blueprints in Berlin. It was paid by the unheralded men laboring in the mud. It was paid by the recovery commanders, walking alongside 3 roaring half-tracks, blowing a whistle to synchronize the clutches of a fragile, 100-foot steel train. It was paid by the prime mover drivers, deafened by heavy engines, terrified of dropping a gear and snapping a rigid tow bar under the immense crushing strain of the load behind them. It was paid by the mechanics and field engineers who waded into freezing swamps, wrestling heavy iron towing eyes and steel cables under the threat of incoming artillery, trying desperately to force the laws of physics to yield to the demands of a broken military doctrine. These men fought a relentless, exhausting war against gravity, friction, and dead weight, long before they ever had to fight the enemy. In the end, they were asked to do the mechanically impossible, and the earth swallowed their efforts. The lasting usual legacy of the German heavy tank program was not an invincible war, machine rolling decisively across a conquered battlefield. It was a blackened, shattered hull resting quietly in a rural ditch or a dense forest. Its frontal armor remained unpierced. Its massive gun still pointed toward a distant horizon, forever anchored to the spit. On a quiet road threatened the permanent loss of an undamaged heavy tank. We first have to look at the severe mathematical mismatch. Ground by a simple mechanical failure, its own army could no longer afford to tow away. Between the armor Germany built and the machines expected to pull it out of the mud, the vehicle tasked with rescuing the stranded Tiger was the Sonderkraftfahrzeug 9, commonly known as the FAMO. When it entered service in the late 1930s, it was an engineering marvel. Weighing 18 tons and powered by a massive V12 engine, it was the largest and most powerful half-track in the world. It was designed with a specific mathematical ratio in mind. It could comfortably tow about 18 tons of dead weight, perfectly matching the early war panzers. When a Panzer III lost a track, a single FAMO could roll up, attach a rigid tow bar, and confidently haul it away. But the Tiger broke that ratio entirely. The heavy tank's 56 tons represented more than a threefold increase in mass. The driver navigates a slight incline, carefully managing the massive Maybach engine. Then, a violent metallic crack shudders through the hull, over the vehicles the FAMO was built to rescue. The problem was not merely the total weight, it was the friction of a mobility kill. If a Tiger was shifted into neutral on a perfectly flat, paved road, a single half-track might slowly roll it forward. But tanks rarely break down on paved roads. They blow tracks in deep mud. They shatter final drives on steep inclines. They slide into artillery craters. When a track locked up, the Tiger ceased to be a rolling object. It became a solid steel block dragging against the earth. The FAMO was equipped with a heavy-duty winch capable of pulling up to 40 tons using a complex block and tackle system. Under ideal conditions, a recovery crew could anchor the half-track, spool out the heavy steel cable, and slowly drag a Tiger out of a ditch. But winching was a static operation that moved the tank only a few dozen meters at a time. It could extract a vehicle from a local trap, but it could not transport it. To move a disabled tank 10 or 20 miles behind the lines, to a railhead or a specialized workshop, winching was useless. The tank had to be towed continuously. The engineers who designed the Tiger had focused entirely on battlefield supremacy. They wanted armor thick enough to shatter enemy shells. The right track locks up, the engine groans under the sudden resistance, and the driver immediately cuts the throttle to prevent a fire, and a gun powerful enough to kill at 2 kilometers. They achieved both, but they did not simultaneously design a 60-ton recovery vehicle to support their new weapon. The military-industrial complex simply pushed the new heavy tank into the existing logistical network, assuming the field maintenance units would figure out how to handle the excess mass. The physical results of this assumption were immediate and destructive. When a single FAMO attempted to tow a disabled Tiger out of soft ground, the physics were unforgiving. The half-track's engine would scream under the load. The clutch would overheat and burn out. The transmission gears would shear off. The massive rubber-padded tracks of the prime mover would spin in the mud, digging the rescue vehicle into its own grave. By trying to save one tank, the maintenance crew would destroy their only recovery asset. A Panzer battalion's maintenance company only possessed a handful of these vital 18-ton machines. Losing even one to mechanical overstrain was a logistical disaster. The maintenance units quickly realized the standard recovery doctrine was dead. The heavy half-track was suddenly underpowered. The tank grinds to a dead stop. Inside the turret, the commander remains perfectly calm. He checks his crew through the intercom when placed next to the new generation of armor. Yet, the Tiger was too valuable, too expensive, and too scarce to simply abandon whenever a gearbox failed. High Command demanded that every recoverable hull be brought back to the maintenance yards. If one prime mover could not physically drag the tank, the mechanics were forced to find a way to multiply their pulling power. They had to ignore the safety limits of their equipment and attempt something the half-tracks were never designed to do. The solution arrived not with one vehicle, but a convoy. To drag the stranded Tiger out of the Ukrainian mud, the recovery platoon dispatched 2, and often 3, 18-ton half-tracks. This was the brute force answer to the mathematical mismatch. If a single prime mover could not pull the tank, 54 tons of synchronized muscle would have to suffice. But linking 3 separate heavy vehicles into a single towing chain was not simply a matter of tying ropes to bumpers. It was an improvised, highly dangerous mechanical ballet. The physical labor began immediately upon arrival. The recovery crew could not use flexible steel cables for a multi-vehicle tow. Everyone is unharmed. He traverses the turret, confirming the hydraulics and the electric traverse are still functioning. The 88mm main gun is loaded and ready. A 56-ton tank rolling freely downhill or braking suddenly would instantly crush the lighter half-tracks ahead of it. Instead, they had to use heavy, rigid steel tow bars. Mechanics trudged through the freezing mud, wrestling these massive iron poles into place. They pinned the rear of the first half-track to the front of the second to the third, and finally, the third to the towing eyes of the disabled Tiger. It created a rigid, articulated train of steel, nearly 100 feet long. Hooking the chain together was only the first phase. The true danger lay in putting it into motion. The operation required 3 independent drivers, separated by thick armor and the deafening roar of 3 12-cylinder engines, to act as a single brain. There was no electronic communication linking their cabs. They relied on a single recovery commander walking alongside the convoy in the mud, frantically using hand signals or a whistle to coordinate their movements. To get the mass moving, the sequence had to be flawless. On the commander's signal, all 3 drivers had to engage their clutches and apply throttle at the exact same fraction of a second. If the lead driver accelerated too early, he would absorb the entire 56-ton load alone, instantly snapping his tow bar or shearing his transmission. The hull, protected by 100mm of Krupp steel, has not taken a single hit. The enemy is miles away. If the middle driver braked a second too late, the massive weight of the Tiger pushing from behind would jackknife the entire convoy, flipping the half-tracks and crushing the men inside. The mechanical tolerance for human error was 0. Once moving, the convoy crept forward at a walking pace. The engines operated at maximum stress, burning through precious fuel at an astonishing rate. Drivers fought their steering wheels constantly, trying to keep the massive tires and tracks aligned in the rutted dirt. Every gear shift was a crisis. If one vehicle missed a gear, the sudden slack in the rigid tow bars would create a violent shockwave through the chain, threatening to tear the towing hooks straight out of the chassis. The German recovery crews were highly trained, and through sheer professionalism, They often made this fragile chain work. They successfully dragged hundreds of immobilized heavy tanks back to field workshops using this exact method. But this success came with a terrifying caveat. The multi-vehicle tow was essentially a laboratory condition performed in the wild. It required straight lines, constant visual communication, and perfectly synchronized machinery. The system functioned as long as the road was wide and the ground was relatively forgiving. The maintenance crews had figured out how to move the weight on paper, but they had not changed the fundamental rules of geography. By every established rule of mechanized warfare, this is a temporary inconvenience. It is a blown final drive, a known mechanical flaw, but a routine one. To understand why this fragile towing chain ultimately dictated the fate of the heavy panzer battalions, we must look at what happened when this rigid train of steel hit a sharp curve, a muddy incline, or the friction of a real battlefield. The synchronized train of steel crept along the dirt road at barely 3 miles an hour, the combined roar of 3 V12 engines deafening the recovery commander walking alongside it. For the first mile, the flat, straight track through the Ukrainian countryside allowed the immense pulling power of the half-tracks to do its work. Then, the road narrowed and curved, sharply around a dense line of trees. The commander blew his whistle, signaling the lead driver to initiate the turn. The driver wrestled the heavy steering wheel, turning the front tires into the curve. But the half-track did not follow the road. Instead, the front tires plowed sideways through the freezing mud. The rigid tow bars transmitted a brutal truth of physics. 56 tons of dead weight, traveling in a straight line, possesses immense inertia. It wants to continue in a straight line. When the lead 18-ton half-track attempted to pull that mass through a sharp angle, the Tiger acted as a massive anchor, dragging the lighter vehicles backward and sideways. To negotiate a tight turn, the fragile chain had to be broken. Mechanics had to stop the convoy, unpin the heavy tow bars, reposition the half-tracks. The commander's confidence makes complete sense. He has trained on medium tanks like the Panzer III and Panzer IV, winch the tank around the corner at an agonizingly slow pace, and rebuild the chain. A single bend in the road could cost hours of exhausted, freezing labor. The terrain presented an even deadlier obstacle when the road intersected the rural infrastructure of Eastern Europe. The combined weight of 3 recovery vehicles and 1 Tiger exceeded 110 tons. A standard wooden bridge over a swollen creek could easily support a horse-drawn supply column or a 25-ton Panzer IV. It would instantly splinter and collapse under the concentrated mass of a heavy towing convoy. Recovery crews were frequently forced to abandon the roads and seek shallow river fords. But leaving the road meant descending riverbanks, plunging the convoy into the softest mud and the steepest inclines. When the multi-vehicle chain hit a wet, muddy slope, the synchronized muscle of the heavy half-tracks evaporated. The 18-ton prime movers relied entirely on their rubber-padded tracks gripping the earth. Pulling a 56-ton block of Krupp steel up a wet 10-degree grade pushed them past their friction limit. The drivers would throttle up, their engines screaming under the maximum load. But instead of creeping forward, the heavy tracks would spin in place. They churned the wet earth into a slick slurry, digging deep trenches into the hillside until the hulls bottomed out in the mud. The entire train would then begin to slide backward, the immense gravity of the Tiger threatening to drag